All right, excellent. So a brief comment on the talk. The subtitle to this talk would be something like an safety engineer's perspective into the introduction to this topic. So as you have noticed from my background, I'm not an expert on this domain, but we're currently trying to make an exploration from the safety perspective into this issue. And yeah, I'll just basically share our progress and our current thoughts on it. And of course, any feedback and comments would be greatly appreciated for us to continue looking into this. So, as mentioned, I'm part of IESE, part of the safety engineering department, and we're reasonably seasoned to sharing our knowledge with the industry and academia, and we specialize in safety assurance. We have a record on in dealing with the automotive industry, and we have a recent interest in autonomous driving. We're experienced in the functional safety IEC 61508 standards, especially 26.2, and we're actively exploring other domains of application such as healthcare, elevator lifts, agriculture, cloud safety, industry 4.0, and dependable AI, as mentioned. We're also developing our commercial tool Safety Box in-house. It's an add-in to EA, Enterprise Architect, and it supports system modeling via UML, SysML, and our own flavor of component modeling, safety analysis via hazard assessment and risk analysis, and component fault trees, a variant of fault trees, and safety assurance via modeling, goal structuring, notation style diagrams. And yeah, this tool is basically our goal to have it expanded with an additional feature, which is security threat analysis for ideally the ISO 21434. So briefly to go over the talk, I'll be talking about some of the initial challenges we noticed in the domain of safety security, what current things we're aware of are being done there, and then I'll go on to talk about how are we going to approach things from our side, which involves embedding this method from the common criteria for threat assessment and risk analysis. How does this fit into Safety Box, and how the concept that we work on in the project that you mentioned, the digital dependability identities, can help us interoperate between tools and more seamlessly transfer the concept across. So, initial challenges that we noticed in the domain were basically that there is a little bit of concept alignment when you just first start into there. There are some fundamental definitions that are relatively well aligned, but there are also some, let's say, corner cases that require specific thought when you approach them as part of an application. So, for example, in some cases, what is considered misuse versus abuse can not be very clear always, and you may have to sometimes not trust the user that if you were looking at it from either the safety or the security domain only, this may have been different. And yeah, basically the two domains need to assign appropriate responsibility to their users and to the operational environment they are in sometimes to carefully navigate this. And in another concern, for example, is that in safety we often have the safe state, but an equivalent secure state may not always be the smartest thing to consider, and may not even be possible theoretically. So there's some issues like these that we have come across, and yeah, we are considering them. So another topic of distinction here is methodologically. From the safety perspective, we've seen that there's a more focus on bringing the risk as low as reasonably possible, which is ZALARP, or practicable, and focus on both passive and active measures for safety. But for security, we noticed that the focus is more on best effort and mainly applying passive measures, as far as we've seen at least. And there's also a different, let's say, weight towards the risk rating systems, where on the safety side, we have things that are typically eventually more quantifiable most of the time, with eventually you can get probabilities and reliability rates and so on, failure rates. And from the security side, this is probably not usually the case. Things are more qualitative there. And we also have design trade-offs between the two domains. So which issue is prioritized, typically safety, but in some other edge corner cases, some other considerations may have to take place, especially, for example, when you have shared resources computationally and physically across the safety security boundary that need to be prioritized. So in a recent mapping study we came across, I'm referencing it here, we note that there is a significant focus in the safety security investigation from the literature towards the phases of requirements in architecture and design. And this tells us that most of the effort is focused on identifying the requirement interfaces between the two domains, and then separating the concerns and isolating the techniques that you apply towards each side. Of course, there's this big non-other area here, which contains a significant amount of publications. And this also indicates that there may be a bit of lack of structure between the two approaches in some cases, and it's not easy to distinguish the boundaries. Also, from the same paper, we noticed that there is a significant emphasis on custom approaches methodologically and on formal methods for doing this kind of safety security co-analysis, whereas the other approaches which are more concrete include the stamp-based approaches, STPAs, STPAs, STEC, and probably also SafeSec, which was not which was mentioned as well, and also argumentation, which we actively support, the Go structure notation, and some other techniques which are more basic. So coming at this from our past experience with the 26.26.2, we know that we have a life cycle of item definition, and then risk assessment to identify what can go wrong with the system, and then we identify how to protect it with safety goals, and eventually derive down to safety requirements and verify and validate the things we had from before. And it's a similar case with the 21.434, so there's a high compatibility here, where the V model extends in parallel to the 26.26.2 V model. And the differentiation comes eventually at the lower levels where the different techniques are proposed. And we think there's good alignment there to proceed in this way by aligning the activities. However, one thorny issue here is how do you synchronize across the two? So if we were to place them in parallel as the two V models like this, we know that we can support some of the activities on the left side of the V model here. And our initial goal is also to focus on the initial stages here on the left of the V model. And at later stages, we'll come back and try to target verification, validation, and make a complete safety and security case. So the combined workflow of all this basically looks like this. We have a set of standards at the start, and this can basically give us our basis for functional specification and risk assessment, and planning the initial design of the system. Unfortunate timing, sorry about that. And for the rest of the system, we can continue with an iterative cycle of architecture design and implementation and verification, and coming back and reiterating where needed. And the final objective would be to eventually arrive at the point where we can have a continuous assessment via a continuous assurance case. But that's a bit looking forward in the future. So with respect to the common criteria, we have an approach that was recommended to us by our security expert, the colleague here. And effectively, it begins by establishing what the stakeholders to the system are and identifying what kind of assets are valuable to them. And then from there, we identify what kind of security needs these assets have in terms of, for example, confidentiality, integrity, availability, etc. And following this, we are able to then specify what the security problem is in terms of what kind of threats can threaten the assets and in which actions they can basically attack the assets with. And then we also know what kind of security policies we can have in place and assumptions as well. And from the remaining set of the problem, which are not already covered by the policies and assumptions to defend against the threats, we can start deriving security objectives and effectively break them down into either system objectives or environment objectives. And there, the rest of the lifecycle can flow by breaking it down into more detailed system objectives and effectively software and hardware objectives at some point, and establishing the security countermeasures to defend against the threats. So shortly, the workflow acts as I described. We begin by identifying some assets. This can be done using, for example, a mind map or other techniques. And for each of the assets, we identify what kind of needs we have for them. And then we can establish a list of threat agents based on generic lists and then refine them as the application needs in more detail. And at that point, we are able to then combine triplets of assets, agents, and actions into combinations into threats and identify a set of threats that we need to defend against, and then assign to combinations of the threats alongside the policies and assumptions we have established, what kind of objectives we need to protect against those threats. And finally, we can break the objectives down into security functional requirements. So this loosely aligns with the 21434 if we consider that the initial stages cover to some extent the item definition and can be informed by that or can establish that. And the threat and risk assessment stage can address the establishment of the threats, of the threat agents, and of the threat scenarios that we need. And the cybersecurity goals and claims can be correspondingly assigned to the security objectives. And finally, we can establish a cybersecurity concept based on the goals and the functional requirements that satisfy them. So, assuming everything is relatively clear so far, I wanted to mention how this is planned to be designed into our current implementation. So our safety box tool currently supports system modeling via UML and SysML, as I mentioned, and we also have our own custom profile, which enables you to model components in Enterprise Architect, and they can be associated with ports. And furthermore, these components can also be associated with a hazard analysis and risk assessment. We currently support a tabular interface for establishing what the kind of functions we need to analyze are, and then what the kind of risks these functions may present based on the hazards that we identify, and eventually reach to the point where we have a safety goal allocation. And finally, and next, we also have the possibility to support component fault trees based on failure analysis. And we can associate each of the components seen in the past image to the corresponding fault trees and do an automatic fault tree analysis. This is possible both via our built-in analysis backend and also via Fault Tree Plus integration. And this is also the possibility for extending this into supporting an attack tree analysis in the future. Next, another feature of the Safety Box tool is being able to support goal structure and notation safety cases. And this is not limited to just safety cases. It can also support any kind of assurance case, basically, which includes cybersecurity cases if needed. So to anyone who's not familiar with this, basically you can structure goals as the high-level claims that you want to establish, properties of the system, and then break it down through strategies of argumentation into further goals or eventually further solutions which provide you with the evidence that you need to argue your claims with. And all of this can be isolated into specific modules which help you manage the complexity of your safety case and refer across modules to different goals. Okay, so this is all well and fine. And yeah, there's a big landscape of not just our tool, but many other tools that do these kind of things. We also saw something mentioned in the previous talks I was able to attend. But the question is, okay, is this everything you need to be able to be effective? And in some cases, we found that as the system grows in complexity and you need to incorporate organizations from multiple parties and even more tools and tools on top of tools and techniques from different domains, things get a lot harder to manage and communicate across parties. So the question is, how do we manage all this heavy information and cross domains and heterogeneous sources of concepts and semantics and knowledge, and combine them into something that we can eventually confirm has confidently built the right system for us? The concept that we developed during the DAYS project is called the digital dependability identity, and it aims to support you in doing that. So using the artifacts that you have developed over the course of your safety and security assurance lifecycle, the idea would be that this common artifact is able to combine these sources of information into an exchangeable format, such that the semantics of the dependability are maintained, regardless of the independent tools or methods that they may have come from. So ideally, it will provide a standardized machine interpretable format, such that it can not only be used by your tools, but eventually it can also be transformed into a form that can be used by your systems as well and consumed. So as we see here, a DDI can be basically combined from the dependability relevant artifacts during development, embedded or associated with a machine in some way. And this can also effectively form a hierarchy with other machines. And the DDIs can be combined together, both at design time and ideally eventually at the configuration and runtime. So how this works is that in principle, we have an association of your hierarchy of systems and components with their own DDI. And each of the DDIs can combine with the others to form a hierarchical DDI. So we have both hierarchy and compositionality supported. And in the more advanced topics that we are discussing, we're also exploring how to make these DDIs executable so that they become part of your running operational system. And the tool chain that we developed during the DAYS project has enabled us to take a first step towards this by using this common DDI tool adapter. So the purpose of this adapter is that you can take each of your tools. For example, you can take SafetyBox and any of the other tools that are mentioned here. And you can use this tool adapter to convert between the common DDI format, either via file or by executing intermediate scripts, and be able to transfer your information across tools and eventually into a combined model, which you can then exchange and reuse. In the backend, this uses the Apache Thrift framework to convert between different languages and interoperate across the tools. And then it gets converted into the common meta model of the DDI, which we call the Open Dependability Exchange meta model. And this also allows us to interoperate by execution of scripts on the fly. So this can happen both during design time and in theory during runtime as well. And it can execute different operations on your either design time system or running system correspondingly. So the holy grail here would be to effectively encode the kind of activities you want to perform during your safety and security assurance as a DDI script that you can then run on top of a DDI. And then you can put together a tool chain of tools that can collect together the results and activate all the kind of scripts that you need to automatically assure eventually the safety and security properties that you want.